The definitions of oxidation and reduction within inorganic chemistry are quite clear and very straightforward. Oxidation is the loss of electrons, the gain of electrons is reduction, and it's pretty easy to tell which has happened. You can look at the electrons in the valence shell, you can look at the formal or actual charges on elements, and you can determine whether a change in the number of electrons has happened, and if so, whether it's more or less. This is not so straightforward in organic chemistry, so we use other definitions. Take a look at a case or two. We'll talk about addition of 2 hydrogen atoms to ethylene to make ethane. In the starting material, there are no formal charges. Everybody has a filled outer shell. Everything looks just great. And you look at the product and you can say the same thing. Carbons have a filled outer shell. There's no formal charges. There is no evident transfer of electrons in one way or another. And yet we call this a reduction. Here's another example. So here's another transformation. Oxidation, reduction, neither? Well, all those atoms have filled valence shells. They don't have positive or negative charges. It doesn't look much like an oxidation or reduction, but in terms of organic chemistry, we define this as an oxidation. What in the world could we be using for definitions to come to conclusions like these? Well, here it is. In organic chemistry, we use the following definitions, and there's 2 for each oxidation and reduction. First, let's say that Z is equal to hetero atom more electronegative than carbon. In practice, this typically means nitrogen, oxygen, or halogen. And within that framework of a definition like that, oxidation is an increase in the number of C-C bonds. Or a decrease in the number of CH bonds. And of course, reduction is just the opposite. So if you look at the examples up above, in this first case, there are 1, 2, 3, 4 carbon-hydrogen bonds, and 1, 2, 3, 4, 5, 6 carbon-hydrogen bonds in the product. There's been an increase in the number of CH bonds, and that fits our definition of reduction. In the second example, there is 1 CZ bond and 3 CH bonds. In the product, we have 2 CZ bonds, and we've decreased the number of CH bonds. So this clearly is an oxidation. We can apply this to lots of examples, and I encourage you to do some practice on this so things make sense to you. Let me just ask you to look at a couple. What would you say about the following compound? Compare that one to the one on the left. They have the same number of CH bonds. They have the same number of CZ bonds. This double bond counts as 2. So this is neither oxidation nor reduction. These two guys are the same oxidation level. Oxidation level is a term that we use to refer to whether something is more or less oxidized. And there's a scale we can look at for reference, sort of helpful. Take a look at methane. The lowest possible oxidation level, it's completely reduced. If you go up one step, so now there's 1 CZ bond. We go up 1 oxidation level. If we go up another step, we're up another oxidation level. We can go another one. We are decreasing the CH bonds at the same time that we're increasing the CZ bonds. And this is a higher oxidation level. There's only one more level you can reach before you're at the very top. So when you look at compounds, you can think of this series, recognizing that here are examples of an increasing oxidation level from most reduced to most oxidized. Another note, when you're adding or losing water, it turns out that you're changing the number of CH bonds and the CZ bonds in opposite directions. So that represents neither an oxidation nor a reduction. And as an example, take a look at this case. If we lost water from this, H2O, we have CO2. Same oxidation level. And there you have it. Oxidation, reduction in organic reactions is simply a matter of changing the number of CZ bonds or the number of CH bonds. And applying one or the other of these definitions to each example will let you determine precisely whether an oxidation or a reduction has happened. One last question. Why do you care? Why does anybody care? Well, chemists care because they often find themselves needing to do a transformation of one molecule into another, of one functional group into another functional group. And you'll have a chance of picking the right reagent if you know whether it's an oxidation, a reduction, or neither. And if you don't know, you'll be doing a lot of wild guesswork. So when you see that something is an oxidation, you'll look at the list of oxidation agents. Same with reduction. If you know it's a reduction, there's only a fairly small list of reducing agents to pick from. So you have a much better chance of being successful if you analyze starting material and desired product and figure out whether that's an oxidation or a reduction or not. And speaking of success, here's why you care. There may be times on exams when you're asked to provide reagents, how you convert one compound into another, and you're supposed to fill in the blank. Here's the reagents to do that. Now, I'm not saying you won't know them, but if you find yourself having to guess, which happens from time to time, doesn't it? You're a lot better off if you know whether it's an oxidation or a reduction, and then pick the reagent from the list of oxidizing agents, reducing agents, or those things that don't cause either. So your success on exams, like success in the laboratory, will be far greater if you're good at determining whether transformations are oxidations or reductions.